Good morning, everybody. It is 10:20, so let us get started. Just two brief announcements so that everybody's getting the same message. I sent out an announcement on Carmen regarding clerical error regarding the BCC 100 plane. I copy and pasted clearly from Simple Cubic 100. I've corrected this erroneous figure. The atoms on the 100 plane for BCC do not touch. The original PowerPoint and your lecture slides that were uploaded shows that they do touch, just like Simple Cubic 100. So I've corrected that slide. I've also added in some more details on Simple Cubic, BCC, and also FCC systems. And that has been uploaded as a supplemental file. So I've sent out that announcement. It should have gone to your email inbox if you set up the notification that way to get announcements from the class into your inbox as they are sent out. If you have not, then please check into Carmen and you can see that announcement, okay? But I'm just repeating it here so that everybody is on the same page, and if you haven't checked it, please do so, okay? And that supplemental file is here. I've also answered a question on the discussion forum about the error. So please check that and just make a note. Obviously, if you work it out yourself, you will have also caught the error. So if there's any clarification questions regarding that particular figure, feel free to ask it now, or you can come up to me after class. Or go to your TA at office hours, or come to my office hours, come to Dr. Brown's office hours, and so on and so forth, okay? And you can post it to the discussion forum if there's any follow-up questions, if that's how you would like to ask your question. Okay, any clarification questions on that? Okay, that does affect your homework. So I wanted to make that very clear before the deadline, okay? So your homework 2 is due today at 5, in case you had forgotten. The other note I wanted to mention is the reorganization of the lecture recordings. As I mentioned, I've made some tutorial videos to go into greater detail and to also to slow down the worked out problems. So please refer to those. Before, I had posted them just in one long line by date to go along with the modules that they follow. But I found that that was starting to be a little bit cumbersome. And so if you're going to the lecture recording section, you can see it's just by date. If you choose to opt in and look at the tutorial videos, they're all aggregated there, okay? So you should see embedded links for how I work out select quantitative problems. Okay. And they're all outlined there. So if you wish, you can Control F, and then you can find if the problem that you have or the question that you have has already been worked out in detail. Okay. Because sometimes I go through strategy in the course, but I don't actually compute the number in the interest of time. But in these problems, especially if it's computationally involved, I do, okay? So we'll talk about methodology here. Sometimes we'll go into detail and actually compute a number. And sometimes we won't. We'll just talk about the methodology. But fear not, it will all be worked out in the tutorial, okay? And of course, feel free to ask me any clarification questions regarding any of these worked out problems as you look through them on your own time, okay? Okay. With that, I'm going to wrap up crystalline structure with module 4, and then we'll go straight into imperfections. So we've talked about crystalline structure for metals and ceramics. Now let's talk about crystalline structures, or lack thereof, for polymers as well, and how that dictates the properties that you experience or that you're engineering for, okay, in your various applications. So we've talked about these long chains. They could be linear, they could be branch, they could be cross-linked, they could be networked, okay? So then how does that affect the crystallinity? We talked about how extremely difficult it is to achieve 100% crystallinity in polymers due to the long chains and the freedom of rotation in the backbone, okay? So then when you can achieve crystallinity, and you absolutely can, they're called semi-crystalline polymers. You will have some areas that are crystalline, and when they do that, it looks sort of like this, where you could see these hairpin turns that I'm outlining in green here over the red. You could see that they'll go back and forth like this. So that's how they pack when they're in crystalline. That's called a crystalline area or a lamellae. And those lamellae structures can also be connected all in the same chain, but have some amorphous regions as well. And so the structure that you often see is what's shown on the right here, where you have areas of crystallinity surrounded by amorphous chains that I'm circling here. And so how does that happen? Really stochastic, okay? Depending on the temperature, the way you cool the polymer, what you could potentially have are crystalline areas like this, and then it could somehow be like this. That's absolutely within the realm of possibility. And so what happens is when you end up with these what happens when you end up with these semi-crystalline materials, you're interested in controlling the percentage of amorphous content or the percentage of crystalline content, which is just 100% minus the amorphous content, right? And so if you have these amorphous areas, certainly you could think about, this would be a less rigid area, and this would pack more closely. So that's more rigid, right? So now you can start to think, okay, well, clearly that's going to affect my mechanical properties, right? Like elasticity, like toughness, right? You can have super elasticity. So there are common examples like rubber band, right? It can be quite elastic, right? And then you have the examples like rubber, right? That's less elastic. It's much more crystalline, and it could be tougher than, say, your plastic bag, which is a linear polymer, linear polyethylene. So you could see how the mechanicals change just based on the chemistry, how the backbone is branch or not branch, and then the ultimate, packing in terms of crystallinity and the structure. Okay. So where do these mechanical properties propagate? And all within, let's say, even the same family. So with polyethylene, if you have linear chains, what we talked about before was something that looks like this. Okay, so this is 2 mers of polyethylene. The hydrogen atoms are going off of the page. I'm going to put square brackets around the repeat unit just to remind you what polyethylene looks like. So that's 2 mers of polyethylene. If I were to continue that, you could imagine, so now I'm just going to draw the carbon-carbon backbone just for sake of clarity. These are now going to be hydrogen, hydrogen, there's going to be another hydrogen here. Okay, so there's going to be, I'm drawing the dots back in. That's the dots for the secondary bonds, right? So you can start to see how they start to pack like that. Now for high density polyethylene, you can achieve that as well by just applying different pressure during the synthesis, right? So high density polyethylene, as you can imagine, you're packing more polyethylene into a certain unit cell. So you're increasing the density, okay? So let me go to a figure that's a little bit more representative pictorially. Here we go. Okay, so here's a polyethylene unit cell. So what I'm talking about is how many of these chains can you put into a unit cell, right? More chains, higher density. Fewer chains, lower density, okay? But it's all the same backbone. It's all the same repeat units, okay? And depending on how many repeat units you have, it will result in different crystal structures and result in different mechanical properties, like low density polyethylene for plastic bags versus high density polyethylene for water containers that are more rigid, or even the pipes that you see, okay? And it's really just all based on how you pack it in. And it results from cooling rates and also from just the pressure that you apply, okay? So that's it. So then, let's say you change the chemistry a little bit. Polyethylene, carbon-carbon bond, 4 hydrogens. What if you change the chemistry? Let's say you change 1 hydrogen to a chloride. Well, where is that chloride going to go? How is it going to be bonded? And how is that going to affect your properties? That goes back to crystallinity. It goes back to the crystal structure of the material, okay? So what do I mean by that? I'm talking about toxicity. So when I talk about this repeat unit here, right, I've taken 1 hydrogen out, and now it's a red R group. And R group is a functional group. That means when you have something else there, it's going to provide you some chemical function that will be different than something else. Here, it could also mean that it's going to provide some other properties in addition to the chemical function. So when you have a molecule like this, the mer here, the way we describe it, we think about the isomerism, so the isomer. And we say, okay, if I draw a mirror plane here, clearly it does not look like this, right? Otherwise, the R would be here instead of this hydrogen, right? So that's going to result in a different chain than if the R's were here. This should also be fixed. Hold on. Oh. So this is to show projection where this is into the board. The E is into the board. It should not be both solid lines like that. It should be dash, triangle. So the D functional group is coming out of the board. The E functional group is coming into the board. Here you could see when you put a mirror plane, those two are the same, right? Or sorry, they're not the same, because when you take this mirror image and you put it on top of this, right, is that the same? And that makes a difference. When they're not the same, it absolutely makes a difference when you propagate the mer into the polymer chain. So, so a polymer is isotactic if it's on the same side. Let's say your repeat unit, all the R's are on the same side, okay? Oops. As you see here. Another type of rendering could be like this. So sometimes you'll see it like this. Sometimes you'll see it like this, where there's a stereo projection. And you could see it more definitively if something's into the plane or out of the plane. But you can see in this example on the bottom left, the R's are all coming out of the plane. It's connected to the solid triangle, right? So the way we describe that, when all the functional groups are on the same side, we call that isotactic. And so if you've heard of the term like isotropy, that means the same. So iso is the same, or isobaric, same pressure, right? Isothermal, same temperature. Okay, so iso means the same. That might not always be the case. Sometimes during the chemistry, the R group, so chemically they look the same in terms of the formula, but the R group can be on the other side, and depending on just the synthesis, if that is your final arrangement on the right side there, the way we describe that is syndiotactic. Okay. And of course, if you have no control during the synthesis for whatever reason, it could be random. And so that's atactic, A being without. Okay. So it is more difficult to pack chains that are atactic than it is for for isotactic. Okay. So if it's all ordered and all on the same side, you have a higher likelihood of actually crystallizing the material than if it's all random. Okay. Because the functional groups might not all align in the same way. Yes? Isotactic, right? Because it's all the same. You want uniformity. So if you think back about, well, the question all the way in the back is isotactic or syndiotactic more likely to crystallize? If you think back to crystallinity for metals and ceramics, right? You think about periodicity. Which one is more likely to be periodic? The one that's all the same to begin with. If all the R's are on the same side, you're going to have a higher likelihood of crystallizing, and it's easier to crystallize than if it's all, somewhat varied and then completely random.
What is the mirror image thing? What does that have to do with isotactic?
It dictates plasticity. So if you happen to put the R group here by design, right? You change the chemistry. Let's say you have the tools to be able to put the R exactly where you want it to put. Let's say you put it here instead of a hydrogen. This is the monomer. It becomes a mer, like this. Great. That's not always guaranteed. Sometimes during the polymerization process, going from your mer like this, and sometimes when you buy from the vendor, there's a distribution, and they'll tell you that. But what if you buy something that looks like this? When you make it a mer, it looks like that. This is not the mirror plane that I'm interested in. This is the mirror plane I'm interested in, because through polymerization, right, this bond, the double bond that was here, forms this bond, and then it propagates like that. So depending on where your R is, which isomer you have, that will dictate how they chain to each other. So let's say you have, somehow from the vendor, you end up with this, and you end up with this. If that's the case, then this is going to be a mer, and this is going to be a mer. And then you would end up with something that looks more like this, right? So do you recognize that this is one of the mers, and this is another mer? Just based on where the R is, from the monomer to the mer to then the polymerized states. But let's say your vendor absolutely guarantees you 100% this. Then you can polymerize it, and it would look something like this. Mm-hmm. Yeah, that's how we describe where the functional group is and the differences in the functional groups. Well, it's based on the stereoisomerism of the mers themselves. It's derived from that. Okay. And if there's follow-up questions to that, feel free to come down after class and we can talk more in depth. In the interest of time, I'm going to move on. Okay. And then there's cis and trans, which is what we sort of talked about but didn't call them then, right? So if both of your functional groups are on the same side of the chain here, right, that could be cis, and then if they're on opposite sides, so this methyl group is not on the same side as the hydrogen here, that's trans. Just same or opposite, just terminology. Okay. Okay. And then I want to also introduce the topic of copolymers. We touched upon this already a little bit. We talked about the randomness or the alternating. If you can control if each mer, from the A mer and the B mer, two different types of mer, how they organize within the chain also affects crystallinity. If something is really ordered like this, like an alternating, black is the B mer, A is the red mer, each dot is a mer. If it's controlled and alternating like that, it's easier to crystallize. For blocks, it's less easy because sometimes you can't control the length of this block versus the length of the second block. So it's less able to crystallize relative to that of alternating copolymer. Okay. And this has huge significance in automotive industry, right? Styrene butadiene, that's in 50% of all the tires that are in the world. It's styrene, 1 mer, butadiene is another mer. And just that copolymer itself, right, dictates the safety of everybody that's on the road, right? It affects friction, it affects puncture resistance properties. It's extremely useful. So copolymers have been around for a while. And so these are the synthetic polymers that I'm talking about. Going all the way back to the 1890s, people have been working on organic or naturally occurring polymers, right? Rubber has always existed from the rubber tree, and people have tapped into that quite literally, right? They've extracted the rubber, and Ohio itself has been a huge contributor to the polymer industry. So just up the road, if you're from Akron, you already know this little tidbit, right? Akron, there's a huge cluster of polymer research because that's where the Goodyear company started, right? Goodyear was the one who took rubber and vulcanized it. He treated it to sulfur, and the sulfur cross-linked all the chains, all the rubber chains, and that resulted in the rubber that was used basically everywhere. And then that has prompted, synthetic rubber to mimic the properties of that. So just cross-linking it makes it stronger. So what he did was he took the synthetic chains, which obviously I'm just drawing cartoonish here, okay? And he treated it to some, that's a sulfur, that's an S by the way. And that's covalently linked to another S, which is covalently linked to this back bond. And one of the reasons why it's angled is because this screen has an offset of about 30 degrees. So I tried to actually draw a straight line, just so you know, and that is what resulted. But the point is the same. When he figured out how to vulcanize, or how to cross-link these polymer chains with sulfur, he changed industry. Like, he changed the polymer and the chemistry industry as a whole. And that's why Akron has made extremely significant contributions in the polymer industry. That's a hotbed of polymer research there, okay? And this was quite revolutionary just on its own. Just the fact that you could cross-link these chains absolutely opened up mechanical properties that weren't available before. And that's just from natural rubber, okay? Okay. So this we've already done in terms of the methodology. So now I would like to proceed with chapter 5, the next module, on imperfections. Oh, I think I auto-played something. Let me see. Or not. I don't know. I'm just going to close this in case something auto-played. Okay. And just a reminder, the last problem that we tackled in polymers in regards to the number average fraction and the weight average, the number average molecular weight and the weight average molecular weight, that's in the tutorial video and that's done in full, okay? Okay. I foreshadowed this, right? I said we're going to talk a lot about crystallinity. We're going to talk about perfection. But as you all know, we live in the real world and our lives are dictated by imperfections. And in fact, it's the imperfections that drive industry these days. It's not so much that you want the single crystal, but it's controlling the single crystal and the amount of imperfections is what makes Intel successful, right? The fact that they can make single crystal silicon and then control the doping amount of how much phosphorus they put in to each silicon wafer so that it goes onto a microchip and that microchip goes into your computer is all dictated between chapters 3 and chapters 5. They figured this all out, right? So they've mastered these 2 chapters and clearly they've made like a multi-billion-dollar industry out of this. So it's not so much that the imperfections drive us, it's the control of the imperfections that control all these properties that you see here, right? Everything, it touches every part of our lives. Diffusion, solid electrolyte batteries, safer batteries, you gotta understand diffusion. Fuel cells, moving those oxygen anions, right? If you want to make a fuel cell car work so that you combine hydrogen and oxygen and make water and reduce pollution, you have to understand diffusion. You have to understand how these defects propagate. Corrosion, embrittlement, right? Vacancy formation, that is all dictated by imperfections. And of course, I just mentioned semiconductors. That's a huge driving force for everything that we have today. Okay, so you may have seen these figures in your book already, right? This is a TEM, or transmission electron micrograph. TEM is actually transmission electron microscope or microscopy, and it's essentially the same thing as optical microscopy. Right? In optical microscopy, you have some magnification and you're looking in on something using just white light, optical, between 400 and 700 nanometers, right? That's the wavelengths of light, optical spectroscopy. But if you have features that are shorter than that are smaller than 400 nanometers, optical spectroscopy is not going to give you the resolution that you need. You need something else that is on the order of something that is small. So if you have a 10 nanometer particle, you're going to need something on the order of that to be able to have any detail that you see here. So any guesses as to what these dots are? I'm sorry? They are crystals. This as a whole is a crystal, yes. This as a whole is a crystal, but the dots are columns. They're columns of atoms. So what you see here in this paper from 2003 is columns and columns of atoms that have all perfectly aligned for you to use an electron beam, go through the sample, and they're in perfect alignment. Do you see how crystalline it is? It's in perfect alignment for you to even see the zone axis, okay? That's amazing. I mean, that's one of the reasons why the 3 inventors of electron microscopy got the prize, the Nobel Prize for even enabling this. And now we don't just use it for crystalline materials, we use it for amorphous materials, looking at glass, we use it for biomaterial, cryogenic electron microscopy, just won the Nobel Prize last year. So this is the forefront of what's to come because understanding bulk is no longer going to cut it, right? Understanding exactly where every single atom is will tell you how your material is going to perform. So this particular material is cerium half, zirconia half, O2. So it's a combination of cerium and zirconium atoms, and O2. And this is a catalyst that's used in most catalytic converters. So if you own a car, if you've seen a car drive by, this has been in it. Particularly, there's platinum deposited on the ceria particles, and that's what drives your high conversion of CO, carbon monoxide, to CO2 so that your car meets emission standards. So you can design the best car, the best F-150 with an all aluminum, one-piece chassis, but if it doesn't pass California emission standards, you're not going to sell any of them, right? So it takes all the properties that you're learning to produce something that is useful for you and for everybody else, okay? And so what makes this material reactive? It's the defects. It's the vacancies, right? So here's a vacancy. So this is a cartoonish image of what's happening on the surface. You see that there's imperfections right here, right? There's a plane here, and then there's a step here, and then there's another interface there. That is what dictates the high reaction, the higher reactivity in this catalysis, in the catalytic reaction, as opposed to just bulk material. So less is actually more. Your platinum nanoparticles will be more reactive and potentially more selective than bulk platinum. You could also introduce other defects, such as substitutional atoms. So here, instead of having all copper, let's say you increase your nickel content. You're adding some nickel into copper. You're causing impurities. You no longer have 100% copper. But that's okay, because if you're engineering yield strength, if you're wanting to increase yield strength, that actually corresponds to higher content of nickel in a matrix of copper, say. And then the last example that I would like to motivate you with is this, right? Silicon. You can have all silicon, but as soon as you dope it with a little bit of phosphorus, it has an extra electron that's shown here that I'm circling. And that extra electron dictates all the electrical and electronic properties that you have in all of your micro devices. Just that one phosphorus atom. Okay. And consequently, if you dope it with, let's say, boron, something that has one deficient electron relative to silicon, that impurity will also dictate and allow you to gate your device differently. Okay. So to talk about the effectiveness and the properties that you experience, we need to talk about it in a formal way. We need to define what we mean by an impurity. What does it mean to have a substitutional impurity? What about vacancies? What happens in real life when you don't have an atom where you thought you would have an atom in your crystalline material, right? And then how does that propagate? Does it propagate along an edge? Does it propagate along a screw axis, mixed dislocations, in a 2D form with grain boundaries? This is the formalism that we'll talk about in chapter 5. So what's the impetus for all these impurities? So someone right before class asked me about energetics. We've talked about energy a lot. We've talked about bond formation. We talked about bond energy curves and how to break those bonds. What does it look like when you increase energy? But that's not the only motivating factor, right? That's not the only thermodynamic term that we have to take into account. We talked about energy. That's the energy of the reaction. That's delta H, right? If you have A and you combine it with B, will it make AB? Right? Will your delta H be negative? If so, great, yes. If not, if it's positive, it's less likely unless you put energy into the system, right? But there's another term, delta S, entropy, that also dictates the equilibrium state of your system. And how we describe whether or not something's going to happen, if a state is going to happen, is with the delta G. It combines both the energetics term, this delta H, and this delta S. Delta S is an indicator of chaos, right? Thermodynamically, things will always tend towards a state of more chaos. If you have a tank of argon and you open it, where are these argon molecules going to go? Are they going to stay in the tank? No, they're going to expand. It's going to create more disorder, more entropy, because now you have more configurational states. Can it occupy this seat? Can it occupy this seat? Can it start to expand? Yes, it's going to create more disorder. That's how the universe tends thermodynamically, right? But we can also form ice. And ice is a more ordered form than water, and that also exists. So you're going to less entropy with ice, right? You're becoming a more ordered system from the liquid state, but that's dependent on temperature, right? So combining all these three terms will tell you if your reaction is going to go or not, if it's going to tend to happen or tend not to happen. If your delta G is negative, it's going to tend to happen. If it's positive, you're going to have to force the system in some way for it to happen. Okay, you have to feed it more energy or whatever it is that you have to do. But your delta G will dictate. So with impurities, you can imagine that's affecting your delta S. If you have a sea of copper electrons, and then you put in one nickel atom, you've changed the entropy, you've increased entropy, because where is this nickel atom going to go? It can go anywhere, right? It can totally disrupt the order of the system. So if it's increasing delta S, it's going to increase the negative component, right, of delta G. It's going to make it delta G more negative. So imperfections are more thermodynamically favorable. Okay? So what types of imperfections can we form? And these are all the imperfections that we're going to talk about. You could lose an atom from a site. That's a vacancy. We'll talk about self-interstitials, substitutional impurities, interstitial impurities, and then if you have pairs of missing, pairs of these 0D or point defects, we'll talk about Frankel and Schottky defects, and then when they propagate to line and area. Okay. Let's look at point defect. If you have a vacancy, it means you're missing an atom that was there. Okay? So you have a system of all the same elements, the copper. Now you don't have a copper where it once was. That's a vacancy. The copper could also move to another site. It could wedge itself into a site that wasn't there. So I'm drawing it in green here. And this atom right here, it just wedged itself into a site that was not the crystallographic site before, but somehow energetically it can happen. We call that a self-interstitial. And so if you think about the compressive strain around the interstitial, and so the strain field is shown in the pink lines there. If you imagine the system for self-interstitial versus a vacancy, what does that tell you about your bond energies within the system around that 0-point defect? So let's think about it. What is going to be more energetically unfavorable? Would it be a vacancy or would it be a self-interstitial? Oh, that's not what I meant to do, sorry. So let's think about it. Let's think about the bond energy curves that we've discussed previously. When you have a self-interstitial, where are you on that energy curve? And when you have a vacancy, where is that relative to the self-interstitial? Feel free to talk with your neighbors. Sorry. Two more. So I'm going to close it. There's also out of time. I just have to move on in the interest of time, but let's discuss it. Okay, so about 76% of you answered this correctly. So let's talk about it, because there are still 30 people that did not answer this correctly. Let's talk about it in terms of the bond energy curve. Where are you in terms of the bond energy? So who answered B and would like to share their reasoning? Yes, Alex. Are you Alex? Sorry, you looked like Alex. What's your name? Bronson. Bronson? Yes. Okay. Sorry, Alex. I don't know. Yes, Bronson. Okay, well, thank you for that. So if you couldn't hear in the back, because the projection is this way, the answer in part was, the analogy is if you're trying to put something, such as a balloon, into a room full of more balloons, that's more energetically unfavorable than just removing the balloon, forming a vacancy. And that would be a good analogy. If you're talking about the bond energy, so if you're not talking about balloons, and you're talking about atoms, we go back to the bond energy curve. So here is the distance between two atoms. This is the potential energy. And here is your interatomic bond distance. That's equilibrium, R naught. So if you were now forcing a balloon or forcing an atom closer to another atom, where are you going to be on this energy curve? I'm going to change to red. You're going to be somewhere here, right? Your bonds are shorter. I don't know if you could see that, so let me just highlight it. So look at this atom that I'm highlighting in red here. Do you see that the bond lengths here it's a little bit closer here than, and you're trying to press the entire system, constrain the entire system into the space, so you end up being closer than what's the thermodynamic equilibrium, your R naught. That's the most, R naught is the most favorable state for your system to be in, right? Now, if you remove an atom, you form this vacancy. Well, where are you on this energy curve? You're going to be in blue. You're going to be over here, right? So then if you change by the same amount, right, if you change in R by the same amount right, or in red, left, the fact that on the right, or sorry, I switched it. The fact that if you follow this red curve, right, you shoot up in energy very quickly. But on the blue side, you're sort of gradually going up. So you're not as high in energy than when you compress things. Okay? So let's look at the vacancy to visualize that. Do you see here this atom in red? It's moving towards the vacancy. It's expanding. So the bond length between this atom and this atom is a little bit longer than R naught. Right? So you pay a higher energy penalty for the self-interstitial than the vacancy. And that's all dictated by the bond energy curve. Okay. Well, how many of these vacancies do you have? Or can you form at a certain temperature? Well, you can predict this by knowing how much energy it's going to take that one atom out, or n atoms out, right? So we can talk about the vacancy concentration at different temperatures, right? And that's dictated by this Arrhenius relationship. So the number of vacancies in your system is NV. And that's related to N, the total number of sites that you have in your material, times the energetics. So this exponential EXP is just it's just natural log E. So you could write it either way. You could write it like this, which you may have seen, or you could write it like this. It's the same. Okay? And so Q is the energy that it's going to take you to remove that atom and form that vacancy. And it's typically on the order of, an EV or something like that. So we're no longer talking in joules, because then you're going to be dealing with a really small number, because we're talking about per atom. So we switch over to EV. And so then we have to switch from Boltzmann constant from joules over to EV as well. And so I have that conversion here. Now, you don't have to remember these constants. You'll be given the constants on an exam, most likely in a data table, if it's not already in the question. So you'll be provided everything that you need, but it might not readily be in the question itself. It might refer you to a data table, and then you can look it up. But it will be aggregated and provided, okay? Because I don't expect you to remember these numbers. Over time, you'll probably naturally just, like Avogadro's number, over time, you just remember it, but for the sake of this class, you're not expected to memorize it. So how do we calculate the number of total sites in the material that you have? Well, we just take the density rho times the volume that you have. So you have a cubic meter, you have 10 cubic meter, whatever it is, however amount, the volume that you have, times Avogadro's number divided by the molar mass. So clearly, this is material specific, right? Different elements have different molar masses. Okay, and obviously they have different densities as well. So the number of sites that are available to you, or N, is going to change based on the material that you have. So we talk about nickel, we talk about copper, different densities, different molar masses, different total number of sites. Okay. So then when we talk about vacancy concentration, what we're really talking about is NV divided by N. And so that's just that, okay? So NV is the number of sites, of vacancy sites. NV over N is the concentration or the fraction, okay? Because that's what we're really interested in, right? If you tell me, oh, well, you know, I have 1 times 10 to the 20 sites, that's less helpful than if you communicate with someone, I have 10% vacancies. Oh, okay, that's really defective. I have 1% vacancy concentration. Oh, okay, that's, you know, you have fewer vacancies there. So we tend not to work in absolute numbers, but obviously we can convert the absolute numbers into the concentration or into the fraction by just dividing out by N. Okay? Any particular questions about this right now? Any clarification before I go on? Everybody written down? NV over N? Okay. Okay. So we're going to actually not do a top hat, but we're going to do this together because I would like to go through the exercise together. So if we are given that this equation here for nickel, the question asks, what is the vacancy concentration for nickel at 1,000 Kelvin? So please be very particular about your units. I'm going to say that again. Temperature is in Kelvin, okay? So if you're given Celsius, you must add 273 to get to the Kelvin conversion. Here, it's already given in Kelvin, and you're told that the formation energy of this vacancy, so you have to put in 1 eV to get this energy out, to get this vacancy out, right? If it was already there, okay? So then that's 1 eV per atom. So we know that Q is 1 eV per atom. And temperature is 1,000 Kelvin. We know Boltzmann's constant. So then we just have to calculate what NV over N is, because that is the vacancy concentration. So if we plug in Boltzmann constant, 8.62 times 10 to the negative 5 eV we get 9.2 times 10 to the negative 6, right? And you can calculate that. So if we do right, so it's actually 9.16 times 10 to the negative 6, rounded up to 9.2, okay? So 9.2 times 10 to the negative 6. What happens if you're at room temperature? Room temperature, let's take it as 25 degrees Celsius, okay? Well, 25 degrees Celsius is 298 Kelvin, add 273. (1.234 times 10 to the negative 17. Yes? 10 to the... it should be... so this is also in your book, but since I haven't logged into Carmen, or I logged out, so please change that. Clearly, we will check for typos when your exam is administered. Okay, but let's talk about that before we leave. At 1,000 Kelvin, it was 10 to the negative 6. At 2